All right, so in this video lesson here, then I am going to introduce the idea of related rates. So let me now write down the title of our discussion here. So we are looking at related rates. All right, but then to have there is no definite meanings. I mean, there is no definite definition of what related rates are all about. So we have to go through an example, and then we will understand the idea about what related rates are all about. But definitely, this lesson here must come after we have a nice and full understanding of what derivatives do for you as a rate of changes. So we have to know how the derivative explains about rate of changes, and then our concept of related rates will come in a lot easier. Another advice from me before we move on any further is that you must also master your skill in implicit differentiation, because the way how I see this concept of related rates is that it is the sort of like the next level of implicit differentiation. So you gotta have that foundation in terms of being able to proceed with implicit differentiation. Okay, all right. So now let me start out with a problem that promotes the situation here. So, and don't worry about related rates or anything like that. Like I said, we don't have a clear definition of what it is. But let me now introduce the problem. Let's say we have an equation, x squared plus y squared equals 9. Okay, and so this is an equation. It points out this equation shows a relationship between two variables. There's variable x and there's the variable y. And of course, these two are related in a way that the square of x plus the square of y equals a constant 9 right here. So we have learned already back in our day studying about how to do the implicit differentiation. Then out of an equation like this, if I ask anybody following with my video to find for me dy dx, then this is at this point should be easy for anyone who has been studying with me and following with my video lessons here, because this symbol is telling us that we want to find the derivative, or another way of saying it, we differentiate but treating y as a function and treating x as the main variable. So that means x here is already, so this is implicitly, I mean, this is already a term that's explicitly defined, but y here is to be understood as some functions implicitly defined in terms of x. And so in that way on, I hope I don't have to recall too far, remind too many steps, but so implicitly taking the derivative on both sides, and yes, we treat x as the left hand side, we have two terms, x squared plus y squared, and then we differentiate, so that's an operator that I also explained a little while ago. We differentiate the left hand side in respect to x, meaning treating the x as the main variable, as the independent variable, and then the y here is, according to the intention here, then it is our implicit function in terms of x. And then the right hand side is the same, but gladly it's only a constant. So differentiating a constant in respect to any variable will give us a 0. And that's the reason why, now allow me to start going a pretty fast pace here, because we have learned this idea already. So left hand side give me 2x for the first term, as usual, as anyone have up to this point hopefully have, if you have already been fluent with implicit differentiation, then you should be able to agree with my work up here. And plus, so that term here gives me 2y times dy dx. Chain rule was part of that to explain how I got that 2y times dy dx. And ultimately, recall for yourself again, we are treating y as an implicit function of x. And so and then that takes care of the left hand side. The right hand side now becomes a 0. And then from that point on, we are going to solve for the dy dx expression right here, and that's how the idea of implicit differentiation was done. Okay, And so the same way, now I'm going to quickly erase the board here because we're not going to relearn about implicit differentiation. I'm just reminding. And so in that way, again, same equations, two variables being about equal rho right there. They are just two variables, any two variables. And I also taught back then in my other video lessons when we were learning about implicit differentiation. Then that idea can carry us into doing dx dy, because now see, if now we are seeing two variables here as two equal rho variables, then x can also be expressed as a function of y right here. So in that way, if we're seeing this notation, the dx dy, that means we're the term now, and I should have mentioned this term in the earlier little problem, but this means we differentiate, right? So the d here means we differentiate. Okay, we differentiate x, right, in terms of y. So we take the derivative, treating x as a function, and so that's why we differentiate x, the function x, in terms of y, and that's the intention of this, the dx dy here. So similarly, let me quickly flash back to the earlier one we've had. This symbol dy dx here, another way of saying that is we differentiate. Right? That symbol tells us to differentiate. Okay, but differentiate what? Differentiate our function y. So we treat the variable y as a function in terms of x. Okay, so two different symbols have completely sort of like opposite meaning right there, but they kind of similar. So now I was in the middle of finding out the dx dy here. So now, as we clearly understand, our goal here is to differentiate x as a function, but in terms of y, treating y as a main variable. Then that means the same equation, but it made our term here, the x squared, now is being so x itself is now to be understood as some implicit function of y. Okay, and so in that way, yes, starting out, easy starts, x squared plus y squared on the left-hand side, I am going to differentiate. Okay, differentiate. So the d notation here, the d operator here is the differentiation operator, taking derivative operator, and then we're gonna take the derivative. We're gonna differentiate the entire left-hand side in respect to, and I already made a little mistake here. We're supposedly doing that in terms of y. Okay. And the right-hand side, again, that constant term being 9, I am going to differentiate that term in respect to y. Okay? And so, regardless of whatever variable that we are differentiating in terms of, this constants will always give you a 0. I mean, differentiating any constant gives you a 0, regardless of what variable we are targeting for. And so now, just like how we did for the other case right here, my first term now, think of the x as already an implicit function of y. So now that means the chain rule is going to explain that we must have 2x as the derivative of the outside, and multiply with dx dy as the derivative of the inside, because x itself, think about the x squared here, is some inside function being x, and the outside function is the square function. So all that idea of implicit differentiation came back. And like I said, again, allowed me to do a lot faster, in a lot faster pace compared to back in the other time when I was really explaining how to do implicit differentiation. And so now this term has already been explicitly defined. And so it's the derivative there, just simply 2y. Okay? And then from there, we're going to do our usual work of taking the derivative, solve for the dx dy here. And then we're going to end up with whichever expression. So my main aim here is just to quickly re-emphasize the idea of that, of how to do implicit differentiation. But now back to what I said earlier right in this video lecture, that finding related rates is sort of like the next level of your implicit differentiation. This is what I mean right here. So, and Once again, feel free to pause the video to really understand what I mean, what my intention is for. You see, the whole dx dy here means the d attached to the x right here means to differentiate. Differentiate what? Differentiate the function x intentionally being regarded as a function of y. And then I also wrote the other symbol around. So I want anyone to have a closer understanding of that symbol here, and in terms of how I, and as far as the way how I wrote it down right here in verbal terms. So now, once we have that idea, let's extend that idea right there. So here I'm not going to say find dx dy or dy dx or anything like that. What I'm saying now is that I want, right from this equation, but I want to differentiate, okay? Differentiate. So I'm writing that term in red ink. And this is not an example, this is an actual problem that I'm introducing the situation that we are facing here. We want to differentiate, okay? Differentiate what? It kind of blank. Because differentiate is only an action, is an operation. So I want to differentiate in terms okay, of t. Okay, take a moment to, or you can pause the video, take a moment to understand what I mean by differentiate in terms of t. All right, so have a close look enough. So now this is what I mean by differentiate. Yes, we take the derivative in terms of t, but what's our objective? See, I'm using that term, what's our objective? Because earlier the dx dy, so you can call, this means differentiate x in terms of y. And so x is our objective. Or if it was a dy dx, then this says verbally differentiate y in terms of x. And this is our objective as y as a function. Our objective here is x is as the function. There's no objective here. It just say kind of abstractly that differentiate in terms of t. Then, so that's the first thing that people start being thrown into, like an ocean of mystery, okay, feeling unsure where to go from there. And then now in terms of t. So similar to these things right here, then see if there's a dy in a denominator, then we call that differentiate x in terms of y. Here is differentiate y in terms of x. So I guess this is in terms of t. That means we treat t as the variable. We treat t as the variable because that we kind of take that idea from how we were doing implicit differentiation and bring that into this. But wait a minute. The variable t is nowhere found in this equation. That's what the problem is. The variable t is nowhere found in this equation. I see an x variable, I see a y variable, and I see a constant. Is there any term here has a variable t? None. Okay, none. And so in that way, this is how I understand it. There is nothing wrong with this instruction of the problem. Differentiate in terms of y, in terms of t. There's no missing thing. And what it says now really means when it says anytime you're being instructed to differentiate in terms of a variable that's completely outside of your equation. And this is how I see it. And this is how I want everybody to see. Every variable that's currently exists in your equation is a function of t. Okay? I repeat. When you have this kind of instruction, differentiate in terms of t, but really your t variable, first of all, you found no objective. No objective. And the variable being indicated here is completely nowhere found in your equation. There's nothing wrong with the instructions. It says what it says here, differentiate in terms of t. But now, first, what's the objective? The objectives are all of these variables. Any of these variables now is being regarded, any of these variables existing in your equation is now regarded as a function in terms of t. Okay? So that means now think of x, the variable, as an implicit function of t. That's the idea right there. Okay, and the same y, okay, as a function implicitly in terms of t as well. So two variables here, two variables x and y are two independent functions, but they are both dependent on the t variable, even though t is not anywhere found in our equation. So in the end, that's implicit definition of x as a function of t, and this is also another implicit definition of our function y in terms of the t variable. And that's why I said earlier we are the work we are about to do, the related rates, they are the next level of how we apply our implicit differentiation technique right there. Okay, so take a moment, pause the video if you have to. Take a moment to understand what I'm pointing out right here. You see, when it says differentiate, when you get that instruction to differentiate in terms of t, differentiate what? See, you're only given an entire equation here, but it could be more than two variables. But then differentiates without any clear objective, right? And then in terms of t, the variable is not even part of the equation. That's what it's intended for. That means we think of x, one of the variable, as a function implicitly defined in terms of the external variable here, the extra variable. And the other variables, and all of the variables, any one of the variables existing in your equation is being regarded as a function in terms of t. I wrote my t looking a little too much like an x right here, but it's a t. Okay, so any of our variable is an implicit function of t. So in case if you need to really highlight that, so this is another implicit. Okay, and this is another implicit function. So these are all, both of these are implicit functions. So I'm going to use a plural. Both of these, the x is an implicit function of t. The y is also another implicit function of t. Okay, and that's is the idea. And so now, after so much beating around the bush, and I hope everybody, anyone viewing my video at this point, have already paused the video and have clear and thorough think through. Then we're gonna take that idea and find the derivatives. So all it says is differentiate in terms of t. And just now I have made it clear that so in this case here, then every variable existing here is a function of t, somehow implicitly defined. We just don't know what it is, and good luck finding out what it is. Really, we don't know. Okay. And so now, but differentiate means, well, right from our equation being x squared plus y squared equals 9. But at least this term I wrote in red has a tremendous importance. Take the derivative. Okay, that's the d operator. That's what the d operator is for. Take the derivative of the whole thing in terms of t. That's what it is. Okay. In terms of t, because differentiate in terms of t. So we got all these two terms on the left-hand side and a constant term on the right-hand side. Differentiate, take the derivative of all of those terms, but in terms of t. Okay, in respect to the t variable. So that means that I'm doing the same thing on my right-hand side. Differentiate that constant term in respect to t. Okay. And so now, again, stay as close as you can with the implicit differentiation, because think of your implicit differentiation as the ground to build into this kind of work. So it doesn't matter how far you go, keep thinking of the implicit differentiation concept in every step of your problem here. Okay? So now that means in my next step, as I keep arguing so many times, this right-hand side here, regardless of whichever variable we're taking derivative for, but our function here, our term here is a constant. So taking the derivative of a constant gives me 0. The left-hand side now, first term is an x squared, but again, x, and I have done this back in the days, back in the video lecture where it was showing the implicit differentiation. It might sound funny, I keep repeating this, but it's very important to understand. X is a function of t. X is a function of t. We don't know exactly what that is because it's implicitly defined. But x is a function of t. The t is the variable as indicated here, but x is a function of t. Okay, so quickly let me bring up a scratch word right here. If x is a function of t, but now I have a square function, and inside of that we have some x, and x is a function of t, so think of it like that. X is a function of t, some implicit function, and we completely have no clue about what that is. But x is a function of t, and this function of t is being inside of some squaring function. Did I give you a hint? Okay, and so in that way, taking the derivative in terms of t, okay, chain rule says we take the derivative of the outside, that gives me 2x of t, right? But for short, just 2x. And the chain rule says we have to take the derivative of the inside. The derivative of the inside. And so what it means now, I'm going to have to multiply with the derivative of x in terms of t. But again, the idea of implicit differentiation lives right here in this problem. We have to, well, x is implicitly defined. So we have no choice rather than just leaving that as a dx dt. This is the derivative of the inside. And since we don't know what the inside function is, we're leaving that as the implicit differentiation, dx dt. All right, so that resolves our first term. So now coming back to my board here, my first term here becomes 2x dx dt. And I really mean 2x times dx dt. Okay? And so now taking the derivative says we can work term by term, right? And that I just now took care of first term. And so now it's time to move on to the next term, finding the derivative of that y squared term. So that means I'm going to add and whatever comes out of that. Let's move on to the other board again to have some quick scratch work. So that means what we're about to do now is to take the derivative of y of t. And again, the term itself is y of t being square. Okay, and now I have to do that again. Y is a function of t. Y is a function of t. And that next term we are about to head out for, back in the other board, that other term we are about to head out for is a square term as well. It's a square term, but it's a square of y. Square of y. And y is a function of t. So it's a square of y. Okay, but y is a function of t. Y is a function of t. And both of these variables, any one of these two variables, x and y, they're all functions of t. And so now, taking the derivative, that's our goal right here, in terms of t, differentiating this term in terms of t. The chain rule again says the derivative of the outside is a squaring. So it's going to be 2y. Instead of writing y of t, I'm just going to use a short symbol, and it is just the variable itself. Okay, and so it's 2y multiply according to the chain rule. Chain rule says we have to multiply with the derivative of the inside. So that means here I'm going to need to multiply with dy dt here. Okay, dy dt. And so once again, why is it a dy dt? Because y is a function of t. Y is a function of t. But we only know it's implicitly a function of t, but we don't know what exactly that function is to write it out explicitly. So that's why the only choice we can have, write that as a dy dt, the implicit derivative here. Okay, and so we're going to take that term and put that into our current halfway done step right here. So the derivative, the differentiation on that term becomes, and of course in terms of t here, okay, that becomes 2y times dy dt. All right. So, ladies and gentlemen, at this point, your work on implicit differentiation has been done, has been finished. Please observe carefully. At this very important point right here, I want to take it slow, and I want everybody to really understand that. Didn't we learn earlier that in some lessons earlier about this, then now we see a derivative as a rate. Okay, take a moment to understand what I'm trying to say. We've gone through video lessons that I really try to explain, hopefully in details enough that any derivative is a rate. And in a more advanced understanding, in a more mature understanding, those are instantaneous rate of change. And so look at right here in our equation. dx dt is the rate of change, the rate of how x changes over t. And the dy dt is another rate of this dy dt is indicating the rate of how y changes over t. So in the end, this equation turns out, as this equation turned out after we used implicit differentiation, then this equation turns out giving us two rates. And so now there are multiple rates, plural, multiple rates being involved in our final equation so far. And so now what I see here now is that this is an equation showing how all my rates that I have found, being related, okay? Because an equation is a relationship between all the variables. So we still got variables involved and equal signs, right? And furthermore, we got rates being involved. And that's how, ladies and gentlemen, that's how now in this current equation that we have found that involves two different derivatives. Now I'm saying that's dx dt, okay? And the dy dt that we have found. These two are, okay, the main discussion title that we're doing here. Related rates. We're not only having one rate in our equation. We're not only having one derivative in our equation. We got multiple derivatives in our equation. And they're all related. And that's what our work finding related rates are all about. And that's the reason why earlier, that was the reason why when I was introducing the discussion topic, I had to say there is no clear definite definition of what related rates means, unless we really have to get into doing one, and we're now going to realize these are rates that are related. Okay? So welcome to the first problem that now you found some related rates right there. Okay? So once we have that idea and starting to pick up with that kind of idea, and keep in mind again, implicit differentiation is the main key that drives behind the scene on any of these problems. Yeah. And of course, so inside of that, we got the chain rule that kind of chain in with these. All right, so I am now going to take a minute or so to erase the board, and we're going to be ready for a couple of direct, or maybe a few direct examples of finding related rates. And after that, the later half of our lecture here, of our video here, is about, I'm going to show you how we applied our skills to find related rates into real applied problems. Real good application problems. Okay. All right, so I am going to get everyone into example 1. And pretty much any of these examples, what I'm doing here now is I am going to start out giving everyone an equation. So what I have here, how about x squared plus y squared equals z squared. Okay, so what I have here is an equation with three variables. Okay, and now how about in this problem, I'm going to say, and you will have a nice full understanding after we got through with these examples right here. How about, so allow me to write in red ink for a couple times. Differentiate, okay, differentiate what? Just simply differentiates. No clear objectives. That's the whole nice things about these implicit differentiation, but being carried into the kind of problem where we are looking for related rates. So we just want to differentiate in terms of t. All right, so pretty straightforward. Okay, so differentiate in terms of t. So that means what? Just like how I was demonstrating in the the problem that was introducing the idea right there, then see the t variable is nowhere found throughout this equation. That means all of these variables are being regarded as they are all being regarded as functions of t. Okay, so quickly a little bit of scratch work here. So that means x is a function of t. Okay, completely implicit. It's even good luck solving for x as a function of t, because there's no way. Okay, y itself is also a function of t, and again, completely implicit. We just know that it's some function of t, but good luck solving for it, because we don't know. We don't know. There's not even a t being involved here. Okay, and yes, z is also a function of t. See, 3 variables at first being involved, but now they're all 3 separate different functions. They are, you can think of them as being completely independent from each other. Maybe they are related, but there are 3 separate functions, and they're all dependent on t. Okay, and so now in that way, how we have a clear understanding of what our goal is, then let's get into it. So let's lay down our equation: x squared plus y squared equals z squared. Every variable now is regarded as a function, an implicit function of t, and good luck solving for those functions. So here I am going to differentiate. So let's go ahead and apply the differentiation operator here. I am going to differentiate the left-hand side, the whole left-hand side, in terms of t. Okay, and now I am going to differentiate the entire right-hand side in terms of t again. And that's what it says, differentiate, right? That's why I'm applying this operator for both sides. Okay, and so now the idea of implicit differentiation carries out again. So I am going to break my left-hand side into 2 separate derivatives. I mean two separate differentiation works, because the sum rules allow us to take derivative term by term. So that means I'm going to need to differentiate the x squared term in respect to t, and that whatever that comes out, I'm going to add with the differentiation of the y squared term in respect to t again, and the right hand side is really pretty much stays the same, differentiating z squared in respect to t. Okay, and so now once again I'm going to quickly step over to my other board and do a little scratch work like that, and then we're going to formulate all the steps together. And really, we have seen this in the introduction problem earlier, so I'm going to be a little brief here. But first term, see what I'm seeing here is a square. So in my first term, we are about to find the derivative here. We are about to differentiate here. Then I'm seeing a square, and the square of an x, square of the x, square of the x. So square here. And then inside of that square is the x variable, but now x is a function of t. Okay, and so that's why in that way, differentiating, or I shouldn't use that prime symbol too excessively, differentiating in terms of t here, then again the chain rule says we take the derivative of the outside, which gives me just simply 2x. But that's not the end for this kind of problem. Chain rule says further we need to multiply with the derivative of the inside. So our inside is here, so that gives me the implicit derivative dx dt. We're good for the first term. Okay, and so, but then allow me to do all these little scratch work all together here. So my next term that I'm about to differentiate, okay, this next term that we're about to differentiate, the term itself is the square of the y variable, square of the y variable. But the y variable is a function of t. Okay, so there in my work now, it's a square term, but it's a square of y, and y is a function of t. Y is a function of t, and so taking the derivative or differentiating that in terms of t, this is what we're gonna get. Again, chain rule says we take the derivative of the outside, which explains for why we're bringing down that 2 right there. So now consequently, we get 2y. And then chain rule says further, multiply that derivative with the derivative of the inside. So this is derivative of the outside, and optionally people can write 2 times y of t. Okay, but that's not really important. And now multiply with dy dt, the derivative of the inside. But sadly, we only know that the inside is an implicit function of t, but without no clue of how to solve for that in terms of t. So I'm leaving that as the implicit derivative dy dt. Okay, and so now that takes care of our term here in the previous step. So now let's move on to that term on the opposite side of our equation. We're going to differentiate the z squared term in respect to t. Okay, so again, and make sure everybody and anyone watching my video here, make sure to take note, because shortly I am going to erase all this little scratch work here. So that term on the other side of our previous equation, then it's a square again. It's a square of the z variable. Okay, it's a square of the z variable. So I purposely wrote it from the outside in, so people can sense the inside and the outside nature of these things right here. And z itself is a function of t. Okay, and so in that way, I am now going to take the derivative in respect to t. Okay, and so again, chain rule says take the derivative of the outside, which gives me 2z. So technically speaking, it's 2z of t, but z of t is just z, and of course we have to understand implicitly z is a function of t by itself. Chain rule says further, find the derivative of the inside, which is here a dz dt. So it gives me a dz dt multiplied with my current 2z. All right, so now we are ready for putting all of these together here. So I'm going to really have to erase my board to make space for my next step here. So all the 3 little pieces have been found. So that means from my previous step, we got differentiation of the first step right here, the first term x squared, and then add with whatever comes out after differentiating the y squared term, and all that, both of those added together should equal to the differentiations out of the z squared term. Okay, so in that way, now putting all the details together, putting the pieces together, we're looking at 2x multiplied with dx dt, okay, plus 2y multiplied with dy dt, okay, and that takes care of the 2 derivatives found on the left-hand side. Let's now move on to the right-hand side. That equals, and now 2z, okay, multiply with dz dt. All right, congratulations. We have now found 3 rates. 3 rates. The beginning instruction of our problem simply just told us to differentiate our equation in terms of t, and now look at what we have produced. Look at what we have produced here. We have produced for ourselves another equation with 3 rates, and all these 3 rates are all being related. So yes, people can go one step further to cancel out the common factor 2 right here. Yes, we can do that. And so our simplified version, the algebraically simplified version of this equation is x as a variable times dx dt plus y times dy dt, okay, equals z times dz dt. But so my point again is these are 3 related rates. How are they related? They are related by this equation. The dx dt rate multiplied with the x function, the x implicit function of t, plus with the dy dt rates multiplied with the y functions, that sum must equal the z functions multiplied with its dz dt. And that's how the 3 rates here are being related. Okay, and so we have just now, found 3 related rates here after differentiating our x squared plus z squared, x squared plus y squared equals z squared here, equation. Okay, so same example, but I'm going to call that part B. So let me now erase this work right here. and I'm going to call that part B. I am going to retain most of the instruction here. I'm going to retain most of the instruction of the problem, but let's call that part B. And so here, seriously, we got 3 different variables. Let me do this. How about differentiate in terms of y? It's just a choice. The point now is that what about, can we pick one of the 3 variables here as the independent variable, and the other variable is now going to be implicit functions of this variable? Sure we can, and that's what I'm about to do right here. See, so now I purposely say differentiates, no clear objective, but in terms of y. So y is actually one among the variables here, but it's okay. It just now means x is an implicit function of y. Okay, and also z is the implicit function of y, but y itself is the variable, and so this term is already an explicit expression of y. Okay, so it's still that idea about implicit differentiation that kicking in right here. All right, so we have 2 functions, x and z here, and they're both functions of y as indicated by the problem. And then this term right here on the left hand side is already a term expressed explicitly in terms of y. Okay, so now let's be ready for work. So at least everyone following with my video have seen the 2 problems. So I'm going to start picking up pace a little bit here. So my starting equation, x squared plus y squared, okay, the left hand side equals z squared as being the right hand side. I am again going to differentiate. So I'm going to apply that differentiation operator to both sides. This time my target variable to differentiate is the dy in the denominator. So it's, we differentiate, that's what the d is for, differentiate the entire sum on the left hand side here in respect to the y variable. Okay, and we do the same for the right hand side. Okay, so that's how it looks for now. So sum rule is telling me, the sum rule for taking for differentiation is now telling me that I can do d of the x squared term, okay, dy, and that equals so let me write that a little higher up right here. So the x squared term, now I can differentiate in respect to y, and the next term is to be differentiated. It's a y squared term, a term that's already expressed in terms of y. So dy of y squared, and all that there equals the z squared term on the right hand side is to be differentiated in terms of y. Okay, and so now I have explained so many times how we found these kind of things, and it's quite similar with my earlier example, the earlier part of our example. So quick scratch work right here. So now the x squared term, we're looking at square right here, but inside of that there's the x variable, but x itself is a function of y, the implicit function of y. And again, even though y is a variable that's already involved in the equation, but there's still no luck solving for y out of something like this. I mean, there's no luck solving for x in terms of y and solving for z in terms of y. No luck with that. So let's give up the idea about solving for x and z as a functions explicitly in terms of y. So all I see here is that the first term there I'm working with, the x squared term, is now regarded as it's a square of the x variable, but x is a function of y. And so now we're differentiating in terms of y. And so now that gives me 2x actually multiplied with dx dy. Okay. And so all that idea, all that explanation, all that reasoning remains the same with how I have done in the earlier part of the example. See, we got the 2x here because of the outside derivative, and chain rule says we have to multiply with the derivative of the inside, and which we had no choice rather than just leaving that as the implicit derivative there. Okay. The next term we're looking at is the y squared term, but gladly y squared term has already been expressed explicitly in terms of y. So now we just do that as the old days, as usual. So it's 2y. There's no need to do the dy thing because it's already explicitly defined. Okay, and so now last one on the right hand side, I'm looking at that z square term. So the way how I see that, it's a square of the z variable, but the z variable itself is a function of the y variable implicitly. And so once again, our job for that right hand side term, we are differentiating. We take the derivative in terms of y. And so differentiating that, it gives me 2z, okay, and multiply with the dz dy. Okay, and so that is now, I'm going to have all these little pieces of details right here and put it all together into my equation there. So allow me to have a minute or so to erase all the work here, because that's just scratch work for us. And so now one more time we're going to quickly look back at that equation here. And then so from that step right here, in our next step we are going to look at yes, 2x dx dy plus, but now it should say 2y, okay, and now equals 2z dz dt. All right, so things are going just that simple. And wait, and I mean this is dz dy, not dt. Okay, that's what I meant. Okay, but now dx dt, I mean dx dy is a derivative, is a rate showing the change of x over the change in y. Okay, and dz dt is another rate showing, I mean the dz dy. I keep saying t. It's probably just a tradition of keep using t for the extra variable. But so dz dy here is the rate showing how z changes over y, over the change in y. But in the end, these two rates, the dx dy and the dz dy, they are two related rates. Yes, you have your choice to cancel out that common factor, but it's not really important. We have already seen our goal here. This equation shows the relationship between the two rates here. Okay, so optionally we can go x dx dy plus y equals z times dz dy. That's our goal right there. We're not really solving for any derivatives explicitly. We just solve for a whole bunch of derivatives, and we land into that final equation where all of our found derivatives are being related with each other. That's the whole point of doing finding out the related rates right there. All right, and so now I am going to be giving out the next example where we're going to have more opportunities to practice our skills in terms of finding related rates. Okay, so here we are at example 2. Okay, and so I'm going to kind of revise my instruction of the example. So here I'm going to say we want to differentiate. Okay. All right, so differentiate in terms of t, okay? And really at this point t is just a variable choice of mine right there. But so in other cases, watch out, it could be s, it could be u, it could be v, it could be whatever it here. So differentiate in terms of t, okay? Each of and I mean for each. So we do this work, okay, for each of the given equation. All right, and so same instruction, and so you can now see my plan for the entire example 2 over here. We will be going, you will be going to, be given with different equations right here, and we are going to differentiate any of those equations given in a problem here in terms of t. Okay, so ready for the first one, part A right here. All right, so our equation can be as simple as how about 5x plus 4y y equals 10. Okay. All right. So this linear equation, and I purposely wrote that on the just in the standard form of a linear equation right here. But so now, if we looking at this equation and combine that with the instruction of our problem, in terms of what to do with this equation, then we want to differentiate in terms of t. And as I pointed out earlier, differentiate, but no clear, no definite objectives here in terms of t. And there's no t variable being involved at all in our equation. So that means x is a function of t. See, just a quick little reminder, x is a function of t. It's a variable, but it's a function, an implicit function of t. Y is another function of t. It's a variable, again, it's the other variable in our equation. And it's now a function of t. And we only have two variables, so here we go. We have two functions, two implicit functions in terms of t. All right, so now from that point on, from that understanding, we are now ready for tackling it down right here. So on my left-hand side, 5x plus 4y, I am going to differentiate in respect to t. That's the requirements of the problem. That's the problem right there. We are differentiating the problem in terms of t. Okay, and the right-hand side is a constant 10 right here, and we are differentiating that as well. We're differentiating that in terms of t. All right, and so after having seen quite a few problems that I'm doing this implicit differentiation, and again, it's intensively that implicit differentiation idea that drives behind the scenes in any of these problems right here. So make sure you get your skill strengthened in being able to do implicit differentiation. Okay, and so the sum rule allows me to find an implicit the sum rule allowed me to find a separate differentiation on that term on the 5x, okay, and add with the differentiation of the 4y term, okay, and then that the right hand side is nothing but just giving me a 0, okay, because it's taking the derivative of a constant, okay. And so now this thing is relatively simple enough. I am going to take a moment to erase my other board, and we're going to quickly use the other board for completing our work. All right, so now one more time looking at this work right here. X is now a function of t, some implicit function of t, and that's all we know. And we have a coefficient 5. Same way with that term. Y is a function of t, an implicit function of t, and 4 is just simply a constant coefficient. The right hand side has already become 0. Okay, so now I'm ready for my next board to complete our work. So my first term would simply become 5, because taking any derivative, coefficient stays the same. So 5 times, so now we have no choice rather than just leaving that as a dx dt like that. Okay, because x is the only term, and it's an implicit function of t that we don't know, so we're just leaving that as the implicit derivative here. 5 times the derivative dx dt. Okay, next term gives me, well, constant coefficient 4 stays the same. The y variable is a function of t, y of t. So now taking the derivative, but unfortunately implicitly, so we're leaving that. We have no choice. dy dt. And the next one here is 0. All right, so now we have found our related rates here. In this equation, we're looking at two rates. They are being related in this relationship right here. 4 times of our dx dt rate plus, 5 times of our dx dt rate plus 4 times of our dy dt rate, and all that here equals 0. Okay, it's a relationship that relates these two rates. All right, so I haven't done in a while any FYT problem for my viewers. So how about right after I finish erasing some of my board, some part of my board right here, and I'm going to put up a problem being an FYT for my viewers. And so feel free to, once you see the problem written up right here, then go ahead and give it a try. But I'm not going to go through the steps. I'm only going to tell you the final answers, the final related the final equation that relates the rates. But I want you, the viewers, or even my students who are studying with me, to try these problems on your own here. Okay, so I'm not going to call that part B, but this is how about we're still part of example 2. But how about let's do a little FYT problem for you to try. F is for you, okay, to try. So how about here I'm looking at y equals 3x plus 5. Okay, 3x plus 5. And so that's our equation having two variables, y and x right here. Okay, let's differentiate in terms of t for that equation. All right, so go ahead and pause the video, take your time. All right, so hopefully you're back and having your own answer, and after you have paused the video and get some work done on that. So the final equation that relates my rates here that I can find is going to be a dy dt and to equal 3 dx dt, and that's all there is. Okay, and I don't think I need to show any steps for that because I intended this problem for my viewers, including my students who are studying with me, to get it done on your own. And if you need any clarification, and find a way to either message me or get a hold of me. All right, so let's now make some more space for the next problem, and we're still in example 2 right here. So allow me to keep bringing up just slightly more and slightly more complicated equation, just more complicated equation as we go on. All right, so part B of our problem. Let me search into my prepared problem bank right here. So how about xy squared equals e to the z right here. Okay, so this problem right here, it's not an FYT. I am going to step in and show the steps right here. So this equation, we have 3 variables. Okay, there's the x variable, there's the y variable, and there's the z variable as part of the e to the z term on the right hand side right here. And the equation here, what we're doing to the equation, we are differentiating this equation in terms of t variable. And again, there's no clear objective. Okay, there's no clear objective. And then the variable t right here is kind of out of nowhere, nowhere involved in our equation. And so that means we're going to treat all of these variables, the x, the y, and the z, as our 3 functions. And they're all in terms of t. Okay, so now before I go on too far, just a quick thing to realize. This is a product between x and the y square right there. Okay, but now from that point on, we are ready. So again, I am going to apply on my left hand side, I am going to apply the differentiation operator to that. Meanings I am going to differentiate my left hand side as a product of x and y squared there. Okay, and in respect to t, and that's what the dt is for. And then I am doing the same thing for my right hand side. I am going to, from where my term being e to the z, I am going to differentiate that term in terms of t variable. Okay, and so now I pointed out this is a product for a reason. We are about to now use a product rule. So the product rule says I am going for that product, I am going to first differentiate. And now remember again and recall for yourself, it's a product of 2 separate functions. One function is x of t, and the other one is y of t squared. Okay, and so now the product rule says we have to differentiate the first function in respect to t and multiply with the other function in the product without the prime, without the derivative, and that's only half of the product rule. The next step, I am going to keep the first function x of t the same. And you can see I scatterly here and there use a term x of t and y of t to remind my viewers that these are really implicit functions of t. Okay, so x of t times, now I'm going to differentiate my y squared here in respect to t eventually. And my right hand side, I'm going to keep that the same for now because nothing much we can do yet. E to the z. Okay, so that's how I'm doing that for my equation term by term right here. And this left hand side completely came out because of that product rule right here. All right, so now again I'm quickly erasing my other board, and we're going to make our way into that. All right, so now a little bit of scratch work. What I see here is so dx, dt of the x term. Our function here is the x, and then we're differentiating in respect to t right here. And that means we're just simply ending up with dx dt. Okay, and so the other term that we have, if we're looking back at that term here, I just want to tackle down immediately with all the differentiated term right there. So this term is a y square, has a y square, and we're differentiating that in terms of t. And so it's a square of the y variable, but y is a function of t right here. And so differentiating that in respect to t, we are looking at, so it's very similar to those kind of work we have done all over. This is 2y, the power rule, but that's only the outside function. Now I am going to multiply with the derivative of the inside, which is dy dt. Okay, and so now with these little scratch work here, I am ready to put all these little details together. Actually, let me roll back a little bit, and I forgot about the right-hand side term. So the right-hand side term, differentiating the right-hand side in respect to t, we got e to the z, but z itself is a function of t. So exponential function is the outside, and then z to the z of t is some inside function of that. And so now this thing here, as we take the derivative, chain rule says we take the derivative of the outside, which gives me e to the z. Okay, because it's the special thing with e to the z, e to the x, e to the whatever. So the outside function is now e to the z, and now multiply with derivative of the inside. Okay, I'm going to use wiggling line right here to indicate that's my inside. Okay, so this is going to be just dz dt, because that's all we know. We know that z is an implicit function of t, but that's all we know. So we have no choice rather than just leaving that as dz dt. So now I'm going to put all these three little pieces in place right here. So our final equation, this is what we get from the, and allow me to one more time swing back to the earlier screen right here. So I am going to substitute that by what we have found, multiply with y squared. So that whole first term now becomes, y squared. I'm writing that in front, multiply with dx dt. Okay, and then I am moving on to my next term. So my next term from the previous equation, it had x and times the differentiation of this, and we just now found the differentiation of the y squared term. And so now I'm looking at x, or 2xy actually, times dy dt. Okay, so I just substituted that 2y dy dt into our term, and consequently we ended up with this 2xy dy dt. And our right hand side now becomes e to the z dz dt. Okay, and yes, ladies and gentlemen who are viewing my video, we are done. We are done in a sense of, in a sense that we have recognized an equation relating our three rates that we have found. We have discovered three rates. There's a dx dt rate, there's the dy dt rate, and there's the dz dt rate right here being involved in our equation. So our equation here relates all these three rates together, and that's why again we call them, these are the related rates. All right, so I'm going to put in another FYT for my viewers, trying to have some opportunity for my viewers to practice independently as you are watching the video. And so there's another FYT. Okay, and so my little equation I've had for you, that I have prepared for any of you, is how about e to the x times y equals z to the 4th power, for example. Okay, and so go ahead and pause the video, work it out, right? And show as much step as, put in as much step as you can. I'm not going to step in for this equation because it's very similar to the one we just finished. And then as you're done, go ahead and resume the video, and I'll just simply indicate the final answers. Okay? All right, so what we're looking at here now is going to be how about e to the x times y dx dt. Okay, and it's a product here, that's the reason why, plus, and now I'm going to leave that here as e to the x dy dt. Okay, and so because we have two variables x and y over here on the left hand side, and our last term on the right hand side is the power rule for the outside, so it's 4z cubed multiplied with the dz dt. And again, without much need to show you the steps, I hope you already had your own answer and agree with mine. Okay? All right, so now let's head out for another problem within our example 2 right here. And as I said, our equation will keep getting more complicated and more complicated as we go, but once we stay very close with that idea of doing implicit differentiation, we will be successful. Okay, so part C of our example. How about our equation now is a natural log of xy, okay, equals C. And I shouldn't use C. How about let's just use that as a yeah, let's use C, but I'm going to make a note right here. C is a constant. Okay. Because instead of writing a 1 or a 10 or a 25 or whatever, I'm out of creativity, so I'm calling that a constant C. So it looks like a letter, but we're not going to use that as a variable here. In other words, we only have two variables, x and y here in our equation. And this, even though being a letter, but it's a constant. Okay. Once again, we're differentiating in terms of t for our equation. It's unclear about the objective. Okay, but that's clearly now telling us that every variable here, x and y, is a function of t. So now I am going to start getting right into the differentiation. So logarithm, it's such a beauty with logarithm. There are a lot of ways to approach that. So I show you one way, and then I encourage you to recognize a different way to differentiate this as well. So we can, it's in the end, this thing here is still simple enough. So I'm going to do this. I'm going to differentiate directly the natural log of x times y over here. Okay, that's one way. And then on the right-hand side, I'm differentiating the constant c in terms of t. Okay, and so this here gives me, see, so right now I can see that I have the product x times y as being inside of my logarithm function. So this part that I underline right here is being the inside part, inside of my logarithm. And so in that way, we have to start using the chain rule immediately. So the left-hand side tells me that the outside being the logarithm, so with the chain rule being used here, derivative of the outside being a logarithm is going to be 1 over whatever inside of that. And so now I'm going to consequently have 1 over the entire product, x times y. Okay? And but now that means now the chain rule says I need to multiply with the derivative of the inside, meaning we take the differentiation of the inside here still as a product. So now that means I'm going to do an extra dt of the product x times y. Okay. My right-hand side will, of course, become 0 because it's a constant, independent with any variable. So regardless of whichever variable that we're intending for, this will always go to a 0 as we take the derivative. All right. So I'm going to head out to the next board again. I'm going to spend about a minute or so erasing it. All right, so now with a little bit of scratch work from what I saw earlier, we need to tackle down what this differentiation is going to give us. See, differentiating in terms of t, but for the product x times y. But at this point, each one of our x and y here has to be a function of t, a function of t. Okay, and so in that way, this is how I see. Product rule says I'm going to have to take the derivative of the first part of my product, the first factor in my product, that gives me dx dt, just that, okay, and multiply with my other function without derivative, and then I am going to add, and so now here I'm going to leave that here, the first function, the first factor of our product being the same, but I'm going to multiply with the derivative of y, so dy dt is here. All right, and so now at this point we are ready to fill this in for our previous equation. So all that I just done on the other board can be substitute for all this. So now I'm ready for my next step of our equation. So concluding our equation from the previous step, then we're looking at 1 over xy multiply with, in parentheses, how about y dx dt, okay, plus x times dy dt, okay, and all that here equals 0. So technically at this point we are done with finding our equation relating the two rates. We got two rates again, right? Two variables at first, two variables that I pointed out at first. There's the x and there's the y because the c is being instructed to be a constant. So two variables here, each one of them is a function of t. That is why consequently we ended up with two rates. That's the dx dt and the dy dt rate. And so now, but I'm not quite happy with this equation, so I would like to now multiply this or distribute this 1 over xy here into each of my terms right there. So distributing the 1 over xy with the first term, the y will cancel. So I'm looking at 1 over x times dx dt. Okay, plus, and now 1 over xy times with that term, the x will cancel. That leaves behind for me 1 over y times a dy dt. Okay, and so now all that here equals 0. And so now I'm more happy. I'm feeling more delightful with this final form of our equation here. But in the end, this our ultimate purpose of these equations. This equation shows a relationship between my two rates, and that's why we call them the related rates. Okay. So, as an extra little gift for my viewers, I want you, my viewers, for my video, treat the same equation here. Okay. Do the same work here, but please use a different approach. Okay, because this is what I mean to use a different approach here. I can give you a little hint because you notice that it's a logarithm of a product. Okay, so we have algebraically we have a property that can handle a logarithm of a product before we take differentiation. So I want you to use that a different approach. And then what I just gave now is only a hint, but whatever approach you use, you should end up with the same equation that's relating our two rates right here. That's why I'm not even gonna, after you pause the video to do your own work, and once you resume, I'm not even gonna show the final answer because we already have the final answer. I just want you to be able to carry through, do the same problem again, reinvent the whole problem again, but use a slightly different approach. Okay, and the approach here is just simply, I mean, one way I can suggest, okay, I already triggered your attention on this. It's a logarithm of a product. So we had an algebraic property for how to kind of reduce the logarithm of a product into something and something, okay, and then you can go ahead and take the derivative in that route right there. But still, we're differentiating, treating each of the x and y here as function of t. All right, and so now before we actually get into some real examples showing the applications of related rates, then I have to be clear that there will be no instructor is able to deliver all examples out there that utilize the related rates, because it's such an unlimited world of applications to related rates out there. So I'll be able to show about 3 examples. And for viewers, if you love to learn more about how you can bring related rates into applied problems out there, just hop on the internet, either hop on the internet or grab a textbook, any standard calculus textbook. You will have a rich amount of problems. And in your daily application, there will be somewhere, trust me, and somewhere here and there will be a problem where you can apply the concept of the related rates into your application. All right, so here we go.